Right, so first of all, I would like to thank the organizers of FroCoS and Tarmo in particular for making this possible for me to present online. I really wanted to be there, but it was impossible this time for me. Okay, now to the talk. I'm here to present this work titled Certifying rlive, a new proof strategy for liveness model checking, work done in collaboration with colleagues Alberto Griggio and Stefano Tonetta from Fondazione Burro Kessler, where I work. So, first of all, just a few words about the field in which we locate this work, which is actually, I think, quite related to the previous talk, so it's really nice to see. So, we are in the field of certifying model checking. So, in general, what is model checking? Model checking is a method in computer science which is concerned with the following problem. We have a model, which is an abstract representation of a real system, and we have a property, the formal specification of a property that we want to check over this model. So we ask this question, which essentially means, does the model satisfies the property? It's a decision problem, so we have a yes or no answer. Now, usually, most model checkers, when the answer is no, the model does not satisfy the property, they come back to us with a counter example, which is an actual trace that then we can expect and that we can revisit of the bad behavior. On the other hand, when the answer is yes, the model does satisfy the properties, model checkers just give us this positive answer there's no counterpart of a counter example in the case of a yes case. Obviously, model checkers are tools themselves. They use quite sophisticated transformation algorithms that are therefore prone to bugs. And therefore, we need to, in a way, trust the result of the model checker. So this is why let's say in the early 2000s, we have this new idea of certifying model checking, which consists in adding to the model checking stage a certification stage. So we would extend or go beyond standard model checking with this idea of certificates, which we already heard about in the last talk, which in general is like we can interpret the word differently, is some kind of evidence validating the yes answer. For the sake of this talk, we would take as evidence a deductive proof again, so a proof done in a specific kind of, in a deductive system. So there are many model checking problems and algorithms to solve them. For the scope of this talk, we are going to focus on a specific model checking problem, which is known as the liveness checking. And we are also going to focus on a particular class of transition systems or models that are finite state transition systems. This can be represented symbolically by a formula giving the set of initial states, a formula for the transition relation, so that tells me how I can transition from one state to the other, and just a set of finite set of Boolean variables. The liveness checking problem essentially asks this question, where these are the finally and globally operator, the natural reading of linear temporal logic. So here I'm asking, does the model satisfies this liveness property, finally globally Q, which essentially means that for all valid path of the model, Q will eventually hold in all future states. So I can have some states in which Q is falsified, but eventually I will reach a point where Q will continuously be true. We can see solving the liveness checking problem we can also see it as like the dual problem, finding a counterexample for the liveness property, a counterexample of this, so the negation of this is this formula here. We would have to find an infinite path because we are concerned with infinite path, where not Q is visited infinitely often, which is what this formula is telling us, globally finally not Q. Since we are in the finite state case, we have that a property, if a liveness property is violated, we can be sure that there always exists a lasso-shaped counterexample, so a counterexample that forms this kind of loop. So the same state is visited more than once. So this is what the model checker would try to find. They would try to find a lasso-shaped counterexample for the liveness property. If he can't find it, then the liveness property is satisfied. Okay, so there are many algorithms for liveness checking. One of the most famous and also most relevant for this work is known as K-liveness, or also a liveness algorithm that counts, which was first introduced in this paper. So the idea of K-liveness is this is the key inside for any valid liveness property in a finite state transition system, there always exists a bound, so a natural number k, such that the negation of the liveness property can become true at most k times, or we can also read it as maybe more naturally, q can become false at most k times. So we can count and bound the number of times the q becomes false if the system satisfies the liveness properties. So this is the idea of k-liveness. Really in a nutshell. So the algorithm will start with k equals 0. We will try to prove that not q occurs at most k times. Then if this check is successful, we can conclude the property holds. If it fails, we increment k and we repeat the process. Every iteration is a safety check, which means essentially we are trying to show that not q is reachable. So it's like is a safety check. Okay, so this was k-liveness. In very recent time, in 2024, for the first time in this paper, we have a new algorithm that has been proposed that is known as rlive, and that has been shown to be quite effective, very effective in proving liveness checking results. The key insight of rlive is quite similar to the key insight of k-liveness. Essentially, we're going to build counterexample to finally globally Q incrementally through a recursive and depth-first search process. The main idea, the new, let's say, idea behind rlive is this idea of shoals. And maybe here you can see the connection with k-liveness. What is a shoal? Is a set of states that can reach not Q infinitely, finitely many times only. So again, this idea of having been able to bound the number of times Q becomes false. So when we search for when the search for not Q reaches a dead end, the safety checker that is within the liveness algorithm will provide us a formula, which is an inductive invariant, that represents the newly discovered set of shoals. Why are these shoals interesting? Because we know that the shoals are the parts of the transition system in which in which not Q becomes true finitely many times only. Therefore, for sure, the shoals are not part of a counterexample to the liveness property. So every time that we find a shoal, we essentially reduce the search space that we have to consider, we have to look, we have to explore. So this is why shoals are useful. So this is the algorithm in a nutshell again. So we will start from the set of initial states and we look for a path to not Q. We continue searching from the successor of each not Q state. In this sense, we go a la DFS. Then two cases are possible. Either a not Q state that I've already visited before is met again, and then I'm sure that I found the lasso-shaped counterexample, so the algorithm finishes and says the liveness property is not satisfied. Or on the other end, no more Q states can be reached, and therefore a shoal is obtained. Okay? Obviously, we are interested in the case in which the rlive algorithm returns to us with a yes answer, because that's the case, remember, the yes branch we want to certify. So in this way, we will have that each shoals blocks part of the state space. We will add this constraint here, which this is just a formula, not C and not next C to the transition relation. And in this way, we will make sure that we won't look at the parts of the transition system that are part of a shoal. So this is just like an example where the liveness property is satisfied. So from not Q, we will search, let's suppose that, for example, we go here, we find the not Q state, then we look from here, we found another not Q state, then we look here, we cannot reach not Q anymore, so this becomes part of a shoal, so we backtrack here, this one can only reach a state that is in a shoal, so becomes part of a shoal, so in this case, basically the whole transition system becomes part of the shoal, eventually, and the liveness property is therefore satisfied. So, okay, so this was what was already done in this paper of 2024 that I mentioned before. This is the pseudocode for our live. For the purpose of this talk, we essentially want to find a way to certify the results of model checker runs every time that our live, that the model checker runs our lives and say, yes, the property is satisfied. So we need to go in some way from the pseudocode to a rule that can be that we implement, that we formalize in a set of deductive rule. And specifically, then we have implemented this in a specific theorem prover. So this is our rule. So it's made of certain premises and the conclusion. The conclusion that you can see here is basically a representation of the liveness problem. So does the model satisfy finally globally Q? Okay, and this formula that you see here, C0 up to Cn, they are in a disjunction, which means the final shoal is the union of all the discovered shoal. Okay. So here I'm going to explain the premises of the rule that I showed before in more detail. So the initial premise, P init, says the following. On any trace, either the shoal is finally entered, so either finally C, or Q is an invariant. What does it mean? If I never meet a not Q state, it means that globally Q holds. In that case, from globally Q, I can essentially infer finally globally Q, so I'm done. So really the interesting part of the algorithm is when I do enter a shoal. So we will explore this case when finally a shoal state is entered. Then this premise P0 essentially tells me that the shoal is initially set to empty, which is what this line of the pseudocode tells you. So the shoal is initially just the empty set. And then we have these two kinds of premises. So we have this premise that essentially says that the invariant C that is incrementally built is inductive. So if I'm in a shoal and I transition, I go to the next step. At the next step, I will stay in the shoal. So in this sense is an invariant. This type of premises, PPI, say something a little bit stronger. It says that if I'm in the shoal and I transition and I'm also in a state where I've met not Q, where not Q is true, then at the next state, this will be true, which essentially means I will be in a shoal that I've already previously built. So in which I know already that not Q can be bound. The number of times not Q has been seen is bound. So the search space can be incrementally restricted as long as we keep visiting not Q states. Okay, so this is the intuition. So we proved, obviously we needed to prove both correctness and completeness of the rule. In some ways, the proof of correctness is the most important. Well, they're both important, but in order to be able to use the rule in a strategy implemented in a proof system, we needed to show that from the premises, the conclusion holds. So that if all these things are true, then the conclusion is also true. Obviously, I'm not going to go into the detail of the proof because it's quite long and it's been done formally in a theorem prover. But I'm just gonna say that the main step of the proof is proving this auxiliary lemma that I've called RLB. That essentially says the following. So we have proof by contradiction. So we assume that we finally enter the shoal. Then additionally, we assume the other premises of my rule. I assume by contradiction that the liveness property does not hold. So remember that this is the negation of the liveness property. And by having these premises, I can prove, and this is the auxiliary lemma, that finally I will enter the final shoal. But the P0 tells me that the final shoal is the empty set. So from these two things, I derive contradiction, and therefore I need to negate my absurdum hypothesis, and I have that the liveness property holds. Okay. On the other hand, there was also obviously the question of completeness proof, because not only from the premises you need to be able to go to the conclusion, of course, but you also need to show that your premises are dischargeable in the sense that your premises are true, so that if the algorithm rlive succeeds in establishing the liveness property through a model checking run, then the model checker is able to come back to us with a set of shoals, C0 up to Cn, such that the premises, once I insert the specific shoals into these premises, once I plug this in, then the premises will be true. Therefore, I know that the premises are true by completeness. I know that from the premises I can go to the conclusion, and therefore I'm basically done. So the proof of completeness has this idea behind it, and is done in the paper, and I'm not gonna go into it for the sake of time. Another thing that is very interesting that we have in the paper is showing that the rliveness, the rule for rlive is a generalization of the k-liveness rule. So you've seen that both algorithms have a shared intuition, which is they prove the same property. Not Q can occur at most finitely many times. In this paper of 2021, we have that the authors show how also k-liveness can be put in the form of a rule of temporal logic. Essentially, they have these inductive invariants, alphas, that keep count of the number of times not Q is reached. In our paper, we show that there is a mapping between the alphas inductive invariant of k-liveness and the shoals inductive invariants of our rule. And using this mapping, rlive can be used to build proofs for k-liveness. So rlive can actually generalizes k-liveness, which is a nice result because we have two different algorithms that then can in a way be seen as two variants of the same idea formally. So this is our proof strategy for liveness checking. We will assume all the premises, so P init up to the last premise. We will apply this lemma that has been proven once and for all. So this is one of the main contributions. It's been proven once and for all in the theorem prover. Therefore, we can use it again as in the strategy, and therefore we can conclude the goal. Then all we are left to do is discharging the proof of obligations, which is proving that the premises of rlive are true. And we will ultimately do it using a SAT solver, or it can be done using propositional methods. And obviously a SAT solver is the most scalable of these methods. P-init is a little bit different. It can directly be discharged by a SAT solver, but it's itself a model checking problem. It's saying that if from this model we can prove that GQ is an invariant. So we will use a subroutine for proving invariance within the main routine for rlive. Okay, so now for how this was the theory part, so how have we implemented this in a theorem prover? Obviously, we had to choose a theorem prover. From previous work, we already have a certification flow for SAT-based model checking algorithm implemented in PBS. PBS is a specification language integrated with a theorem prover. It's mainly interactive, but it also supports strategies developments. So we say that it's clear that we need to do some kind of temporal reasoning for representing rlive, and therefore we have a shallow embedding of LTL into PBS. This is just like a snapshot of some LTL concept like a trace or an LTL formula or connectives, how we have done them in PBS. Okay, and then finally to our certification flow. So this is our certification flow. We have the model checking stage, which doesn't really change. And this is very important because it means that our certification approach can be implemented on top of most model checkers. So we've used in particular nuXMV because nuXMV has got an implementation of rlive. So we start with the original problem. Does the model satisfy the liveness property? The model checker runs, says, well, in this case, we are interested in the yes case, and comes back to us with the set of shoals that he has computed. So the model checker needs to be extended only in the sense that he needs to be able to give us, dump us the shoals, but these shoals are already computed anyway, so it's really a minimal modification. Then we generate a formal theory representing this problem. So a formal theory in a target language representing the model checking problem. What target language? The language of the theorem prover of your choice, which in our case is PBS. So we have a simple Python script that goes from Eiger to PBS because Eiger is the format that the nuXMV uses. one of the formats. And then finally, the theorem prover kicks in with its reasoning engine and with the specialized, augmented with the specialized strategies that we have developed and that I've shown you earlier, and carries out a proof of the main theorem, where remember this theorem is the formal representation of the original model checking problem. And within this proof, it will apply the rlive lemma, which again has been proven once and for all, so we can just instantiate it with the shoals that the model checker has given us. Okay, now into the experiments. We have experimented our certification flow on benchmark sources from the hardware model checking competition. So, you know, realistic benchmarks, some of them even quite big. So we have tested it on 50 problems in total. 41 were successfully certified within the time and memory limit. The rest went out of memory mostly. These charts, I think we demonstrated in this way the feasibility of our approach, but from these charts we can see some performance gaps. So here we are comparing the model check-in time against the PVS total proof time. So the time that the model checker takes to say yes against the time that PVS takes to perform the proof. And we can see that the model checker takes longer. On the other hand, we are comparing the model check-in time with the IX time, where IX is essentially the SAT solver within PVS. So essentially this part is the discharge of the proof obligation part, which is the most creative part in a way of the proof, the new part of the proof, the part that is always different between models. And we can see that actually this is much better than this situation, although there is still some scalability issues. So we did some deeper analysis on what are the bottlenecks of the proof, and we've realized that we have like essentially internal bookkeeping and definition management bottlenecks within PVS, which is in a way is normal because PVS is mainly an interactive theorem prover, and he has to carry out very rigorous checks before going back to us with a proof. And in certifying model checking in general, there is a little bit of this like trade-off between scalability and reliability, as we also have seen from the previous talk. But in general, our framework is not dependent from PVS. So as future work, we would like to either explore maybe implementation in theorem provers that are more optimized for automation, or maybe optimize PVS for this specific use case. Also, the main contribution of the work is the theoretical foundation and the proof of correctness of our liveness strategy. And then as a final slide, just to conclude, what are the achievements and what future works we would like to tackle. So the key contribution were to develop this novel proof strategy for certifying liveness check-in results when the liveness check-in results were carried out using in particular the rlive algorithm. We showed that despite the complexity of the algorithm, if you go and see the algorithm, you'll see it's quite complex. The shoals provided by the model checker are sufficient to generate the proof. So there is really minimal model checker modification. The model checker does what it's already doing. It just needs to come back to be able to give us the shoals that it computes anyway. So in general, we believe we achieved progress in the field of certifying model checking as we have distributed the trust across more fundamental principles and created redundancy that increases the overall confidence. So the model checker says yes, and here is a proof of it. Obviously, you don't eliminate the need in trusting something at all altogether. That's not possible, but you split this trust across principles that are more fundamental. And as future work, we would like to extend the model checking approach to other liveness algorithms, for example, liveness to safety or FAIR. And we would like to see if we could actually have a strategy that encompasses them all, just like we have seen that the strategy for rlive can include proofs for k-liveness, so two algorithms under the same strategy. And another thing that we would very much like to do is generalizing this certification approach also to the infinite state transition system case and SMT, because rlive has been extended to deal with, very recently, to deal with infinite state transition systems. And that's it for my talk. This is just some bibliography that I mentioned in the talk. Thank you very much.